Welcome to a new topic. We are going to look at linear regression in particular. There is another topic called nonlinear regression, which we will just barely touch upon, but we will not get into much detail. We will focus on linear regression. Now, what we are going to do is we are going to solve the familiar problem, but here the roles of what is measured and what is to be estimated changes. For example, we have been looking at systems of this particular form, ax is equal to b for the linear case, and you can always represent this as ax minus b is equal to 0, and we can also in abstract form represent it as f of x is equal to 0, where x is the unknown, right? We would know a and b, and then we would find out x, and f of x in this particular case as this linear form. We also looked at systems that can be described by this form, in general nonlinear, right? F of x beta is equal to 0. We knew the function form, right? The nonlinear function form. We knew the values of beta, and then we tried to find out the values of x. A particular example is the adiabatic CSTR problem, where we tried to find out, given the values of alpha, beta, gamma there and the mass and energy balance equations at steady state, we were able to find out the dimensionless quantities, dimensionless concentrations, in particular x, and dimensionless temperature y. So we have looked at cases where the function is known, the parameters are known, and then you have to find the unknowns, right? So we have looked at both linear and nonlinear problems in that regard. For linear problems, we found out the unknowns using three classes of methods: the decomposition methods, the iteration methods, as well as the direct methods. For nonlinear equations, we looked at the Newton method in particular, and we also looked at the bisection method. Now we are going to handle equations of the same type, but what is unknown changes. So we are going to look at systems of the form in general y is equal to f of x beta, and f here can be a linear function or a nonlinear function. Okay, so if it is linear, of course things simplify quite a bit, the mathematical calculations simplify quite a bit, and you may be even able to solve by hand. But if f is nonlinear, things get a bit complex and you have to use computers and computer algorithms to solve the problem. In any case, the problem is y is equal to f of x comma beta. Now, y is what is called the dependent variable. X is called the independent variable. If there are a bunch of x variables, then there will be several independent variables. And f is a functional form that could come from mass, energy, momentum balances, or it could just come from the modeler, because the modeler might say, I expect the relationship between y and x to be of this particular type. And these models will have parameters which are beta. The parameters beta can have a physical meaning. For example, it could represent activation energy, frequency factor, heat transfer coefficient, biomass growth rate, catalyst activity, things like that. Or these could just be coefficients that are introduced by the modeler. All right. So beta is a vector of parameters, some of which or all of which can have a physical meaning, or none of which may have a physical meaning but may have a mathematical validity. So what I'm trying to say here is a model of the form y is equal to f of x comma beta will be handled here. Y represents the outputs or the dependent variables. X's represent the input variables or the independent variables. Beta represents the parameters in the problem or in the model. And f is a particular form of the model which you obtain from either first principles or which you just hope will work for you. Now, in this case, what is going to happen is the f form is known typically. There are problems where you can also find out the f form, the form that the function takes, but we will not get into those things here. So we will have situations where f is known, a form of the equation is given to us. That form of the equation will involve symbols x and beta, and we will have measurements of x. we will have the corresponding output measurements y. So the parameter vector is the question mark here. We do not know the values of the parameters. We have a functional form, we have measurements of the output, we have measurements of the input. Then the question is, what is the value of the parameters that are in the model? What are the best values of parameters in that model? So that is what parameter estimation in general means, right? This broad area of parameter estimation is very, very important. In this particular case, we would look at primarily linear regression methods to find out the parameters of linear models, or what are called linear in parameter models. The extension to nonlinear regression, at least in the case of algebraic models, is not difficult. As you can imagine, once you enter into the nonlinear world, one of the key machineries that helps us to solve the problem is going to be the Taylor series expansion, and particularly the Jacobian, etc. So let us start with linear regression. So this topic is an important topic and a compulsory topic. I will also put up a video from one of my past courses on nonlinear regression. The nonlinear regression part will be optional. In fact, you don't have to touch it if you don't want to know about it. But if somebody wants to know about nonlinear regression and how to estimate parameters in nonlinear regression models, you can easily follow that video and get some idea about it. All right, but please note, whatever I'm covering as part of this lecture 7 linear regression topic is important for this course. Now, this is how we have the data from the field. It could be from the lab. Somebody goes to the lab and does experiments at certain values of the x variable. So x could be the coolant flow rate, and y that you see there could be the product composition of a particular species. So what you do is you go to the lab, follow a good protocol, and then you change the input variable, right? For different settings of the input variable, x is equal to 1, x is equal to 2, x is equal to 3, and so on, you are measuring the corresponding output variable, and that is what is tabulated here. So when I did the experiment at x is equal to 1, this value, I get y to be 0.5. When I do the experiment with x is equal to 5, the output measurement is 3.5. So this is what this table contains. And kind of nobody tells you what is the model relating x to y. So if you plot it, you will find this data translates to this plot. And this is easy because you have one x variable and one y variable, and we know how to easily plot it and visualize it in a two-dimensional graph. That is what you see there. What somebody can hypothesize based on this is that the relationship between x and y is linear, and somebody could eyeball it and draw a best fit line like that, or use a computer program or whatever to find out the equation of this line, and that equation of the line will serve as a model for the system. So basically you visualize and then you hypothesize a linear relationship between y and x, and you find out the value of the slope and the intercept that is the best for this given data. Now somebody could be greedy and say, well, I want the model to go through all the data points. If you look at this line that I have sketched there, the line passes through the cloud of points but does not pass through any of the data points that you see there. All right. So somebody could say, well, we expect models to follow the data trend perfectly, and therefore I would go for a sixth order polynomial, and I can fit this model that you see there, right? A very curvy model, right? A sixth order polynomial will have 7 parameters, right? So a line has 2 parameters. A linear model, a linear polynomial has 2 parameters, slope and the intercept. So a sixth order polynomial will have 7 parameters, and if you estimate all the 7 parameters from the data, what you see is the resulting polynomial will go through all the data points perfectly. So this is what is called a perfect fit to the data. But you can see that this polynomial is rather wavy. Even when you interpolate it within the range of the experimental data, x is equal to 1 to x is equal to 7, Even within, it shows a lot of waviness. This sixth order polynomial will be good if the data does not have any noise. All right. But unfortunately, real world data has noise, and it is not a wise idea to overfit the data, because we can understand that each data point comes with a certain error because of many things, because the sensor was not placed properly, because the sensor has bias, and there are other interferences that makes the measurement wrong. So just as all models are wrong in the sense we cannot perfectly capture what happens in the real world with a model, likewise all data is faulty. That means all data is corrupted by noise. So there is a problem with the model, there is a problem with the data as well. If we are able to measure data without any error accurately, that means without any uncertainty, then the world will be much better off. But unfortunately, nothing can be measured without error. So, fitting a sixth order polynomial to this data set seems to be a case of overfitting. Overfitting means what you do is you also model the noise, which is not a good thing because you want to model the signal and leave out the noise. You understand? We do not want noise to be fitted into our model equation. We acknowledge the presence of noise, but we do not want the noise to corrupt the parameters in our model. So whenever you overfit, this is called over modeling, you are fitting in the noise into your model, which can be quite detrimental because your parameters in the model will become very imprecise. On the other hand, when you model with data or otherwise, right, whenever you model, you can also do under modeling, which means you don't even capture the signal properly. You grossly under model the phenomena. This is quite possible. That means I go for a very simple or a very simplistic model. That leads to under modeling because you are not even capturing the signal part of the data or what the world reveals to you. So whenever you model right, there is always a danger of underfitting. That means you're not even capturing the phenomena properly, or you overfit. That means you're capturing more than the phenomena. So modeling is a very fine line between under modeling or underfitting and over modeling or overfitting. That is why there are many measures that tell us what is the best complexity for the model. This is a very broad issue, and as long as you acknowledge that there is problems with both the models and with data, we are fine. What engineers do is basically handle uncertainty in the best possible way. There's going to be uncertainty in data and in the model. The question is, how do you model the most important things as accurately as possible without overfitting? That's what makes the job of the engineer interesting. And what you see on the right panel here is the best fit line, right? The thick line that you see passing through this data point cloud, that is the best fit line. It has got two parameters, the slope and the intercept. It clearly acknowledges that the data is noisy and there is no need, or it is even dangerous, to make the model go through all the data points as was done here. This can be dangerous, and in fact is dangerous with noisy data. So as Einstein said, everything should be simple but not simpler. That means you must keep it simple to avoid overfitting, but you cannot make it too simple to create the underfitting problem. So looking at the data, this best fit line may be a better description of the experimental system as compared to this. But if you promise me that there is no noise in the data, maybe something like this would work. So given this data set and this visualization of data, I will just go ahead and propose a model of this type. Y is equal to A naught plus A1x plus E. A naught is like the intercept. In school, we would call it as C. A1 is the slope of this line, which we would call as M in school, right? We know the familiar model. Y is equal to mx plus C. Of course, this term E may be somewhat new to us. In school, they probably talk about it, but they may not elaborate upon that. This E is our acknowledgement of the presence of noise in the system. So what we would call as measurement or instrument noise is one component of this. This E also quantifies our ignorance about the system. That means we may have other variables, Z, R, etc., that affects Y. Even though we try to control for those values during the experiment, that means we keep them flat. That means we make sure that other variables don't change as we collect this data for this experiment, X, Y. There could be other things that change subtly and that could cloud the measurement of Y, etc. So that kind of variables that we don't capture in our data set is also reflected in E. And who says the model should be A0 plus A1 x? It could be A1 x to the power of 1.05. Pretty linear, right? Or almost close to linear, but it need not be x to the power of 1. It could be x to the power of 1.05. So there are structural mistakes that we might make. Even though this looks very linear, we have force fitted x to the power of 1 to this model. So any structural problems, any variables that we have omitted, any instrument error, all of these are captured in E. So E represents all the mistakes, ignorance, etc. So this part, A0 plus A1x, is the signal part. This E is what is called the noise part. So we are saying the responses Y that we see in the system is due to a signal. That's the true value of Y is this, the signal part. And that is corrupted by this E part or the stochastic part. So that is an acknowledgement of reality, that there is a signal and there is a noise part to our data. To just summarize what we have looked at so far, this is the data that comes from the field through proper design of experiments. Once you get the data, if it is simple one x variable and one y variable, so this is called the univariate regression problem, one x and one y, then we can visualize it. And then we can say, well, I'm going to propose a model of this type because it seems like the data falls along a line. And this is the equation of the line. Y is equal to an intercept plus a slope times x, plus I recognize a noise part, which I denote by the symbol E. And now using Y and X data along with this model form, I'm going to be able to find out the best estimates of parameters A0 and A1. What is the best slope value? What is the best intercept value? And I also want to find out some characteristics of this noise E. Because when we write this model and use the mathematical machinery that we will introduce in the next few videos, we are going to make some assumptions about E. That E is normally distributed. E comes from a normal distribution with certain mean and certain fixed variance. And we assume that the error E for each experiment, in this case we have done 7 experiments, for each of the 7 experiments the error is independent of the errors in the other experiments, etc. So we're going to make some assumptions about E in arriving at the answer, but that is for the statistics part, so you should learn that in a statistics course, or you have already learned it. So I'm not going to dwell into that E part very much, except to just outline some measures of E. But what we are going to look at in the next few videos will be based on assumptions about the characteristics of this noise E. When you have one X variable and one Y variable and the model is like this is called simple linear regression or SLR. Sometimes our model may not be this simple. Let's say we see a quadratic trend in the data. That means there is some curvature in the data. When you plot this experimental data points on this Y versus X chart, right? Let's say you plot it, and then sometimes let's say you see a behavior like this. So we see there is a curvature in the data, right? Just by eyeballing, we know there is a curvature in the data. So I might propose a model of this type. Y is equal to A0 plus A1x plus A2x squared plus E. So we have the intercept, we have the so-called slope, we have the coefficient of the quadratic term. So there are 3 parameters in this model. So this would not be called simple linear regression any longer. The mathematical machinery is the same, as we shall see later, but this would be called multiple linear regression or MLR, right? Because you're going to have multiple X variables, so to say. So this behaves like X1, this x squared behaves like a new variable x2. So it is also written in this form sometimes: a naught plus a1 x1 plus a2 x2 plus e, where in this particular case that I've shown here, x1 equals x and x2 equals x squared. That means I'm creating a new variable x2 by taking the squares of the values of x, right? And then I can write it in this form. Sometimes this form may arise very naturally. For example, if you take a distillation column, right, which has got a feed, which has got a product stream, a vapor stream, and a liquid product stream. Now, what can happen is if I'm trying to get a model for the composition in the distillate stream, that composition may depend on the feed composition. It may depend on the amount of steam that I put in the reboiler. It may depend on certain other characteristics of the system, right? For example, you can see that the temperature of the top tray predicts this overhead composition very well. So in this particular case, I can take the feed flow rate F as x1, I can take the steam flow rate as x2, and maybe I can take the temperature in one of the top trays in the distillation column as x3, etc., leading to a model where the top composition Y is a, let's say, a linear function of the feed flow rate, of the steam flow rate, of the temperature at the top of the column, things like that. So that will also lead to a model of this type, and then we will have to call that as the multiple linear regression problem. So the problem in general can be a simple linear regression problem or a multiple linear regression problem. The mathematical machinery is the same as long as we live in the linear world. We will explore these things in the subsequent videos. Thank you for your time.